Lecture 26, Finding Bottleneck Devices. Okay, at this point we had a little discussion on the subject of load testing, and we kind of have some idea around what it means to validate that something can meet an expected workload. The example I kept going back to was around the CFO wants to know, can we handle 10 times as many users? And yeah, we have some way of approaching that problem with load testing. But one of the things that we're going to find as we explore validating the performance of anything is, what's our limiting factor? What's the bottleneck device? So studies show that poor mobile app performance, whether that's due to high usage of resources, consumes a lot of battery, or it's using a lot of memory, what have you, or it's just plain slow, is a major complaint in App Store reviews, right? There's a linked paper in the notes. It's older at this point, but I don't think that makes it irrelevant, right? And there are kind of hilarious reviews that look like this. My Legos came broken, what have you, and yeah, of course that's a little bit silly, right? But here's a review. Admittedly, it's from 2013. But it really gets to the heart of this, right? Like, it's a 1-star review, thinking of uninstalling since updating my favorites don't show up at the top of the page, or they highlight in the app is painfully slow. The blog keeps resetting back to the matchup page, so I cannot access any play-by-play. I honestly don't even recall what app this is a review for, and it doesn't really matter, right? But that's like not a satisfied customer, right? We might like to think that a user is able to give us some idea of what's wrong, but often they don't, right? And I'd like to think also that automated testing has made it easier to catch these kinds of things, and we can automate the idea of performance testing, but often we don't. And I would guess that a distressing number of issues, even to this day, are still found as a result of complaints from the users when they give a negative review. And sometimes that negative review looks something like 1 star because it's not possible to give 0, that sort of thing. Okay, so from a bug report, especially one written by a non-technical user, how do we make use of that, right? Like, we might have a vague idea of what's wrong, but that might not be sufficient for us to track down the nature of the problem, and we need to investigate quite a bit more if we want to have any hope of actually solving it, right? If we're unable to localize the problem, we just waste time, doing stuff that doesn't work, right? So usually we are going to assume that it's the CPU that's the problem. And in fact, our next topic in profiling is going to focus on CPU as an area, right? That's usually the case, and I mean, this particular meme was contributed by a student from previous year, in which, like, yeah, of course, we can easily write a program in which CPU is the limiting factor, and if I simply had more CPU, then CPU load wouldn't just jump to 100 and stay there, right? Future topics will mostly focus on the CPU profiling side of things. But that's not the only thing that we're going to talk about, and we will consider other kinds of profiling as well. But onward. In the words of Sherlock Holmes, as written by Sir Arthur Conan Doyle, it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. Okay, this picture is Jeremy Brett from a late 80s Sherlock Holmes adaptation, which I think anyway is really good. You may prefer Benedict Cumberbatch kind of approach. That's fine. But certainly I think the Victorian setting for the Jeremy Brett one, and closer adherence to the source material is the kind of thing that people who like the original Sherlock Holmes rather like. But yeah, what we mean by this is thinking about collecting evidence before reaching conclusions, right? If you get told that the app is slow and you just jump to the conclusion that it must obviously be CPU, that could be wrong. That could be wrong. We don't know, right? We'll only find out by actually sort of doing an investigation. And I put up here 5 things for us to look at. And these are things that are potentially our limiting factors, and they are categories rather than specific causes. Now, when we look at those, right, they're listed in numerical order, and that's the order in which we're going to talk about them today. It doesn't mean that this is the order of likelihood of the source of the problem, if that makes sense. There's different circumstances that apply depending on the nature of your application and what it does. There are many things that are more CPU intensive and many things that are more disk intensive. So yeah, jumping to conclusions here just based on the order of the list is not sensible. But for our purposes, we need to go through them in some order today, and this is the order that we're going to choose. You don't have to investigate them in this order if you don't want. Now, fixing the problem, once you've found it, is a separate issue. It involves the application of techniques covered elsewhere in the course. That might be really difficult. Sometimes the user's device or hardware is just too old, right? Or lacking important hardware that would accelerate it. Games are the most obvious example of situations where the minimum and recommended hardware configurations are published, and if you don't meet the requirements, then you're going to have a bad time if the game runs at all. And there are people who are willing to play games that look more like slideshows than any other medium. I can't say I'm one of them, but people will make do with the resources that they have, and if they don't really have any choice, well, then they don't really have any choice. But for the most part, right, this applies to apps as well. When you are creating an app, you can say we're dropping older devices from the supported set. Now, that's more likely the result of the device no longer getting OS or API upgrades rather than being too slow. And this is totally possible as a choice. We could say, yep, the device that you have is too old. We only support devices that run the most recent 3 major OS updates. And if your device is too old to get one of those, well, then it's too old to run this application. And you are cutting off some users. These are people who want to use your product and want to use your software and may even be willing to pay for it, but we don't support it. But on the other hand, that might be preferable to them having a bad time. If the device is simply too slow and the app is going to run terribly and they're going to have a bad user experience and they're going to leave you a negative review that perhaps steers other people away from using your thing. It's not great. It's not ideal to give them what they think that they want when clearly they're just going to be unhappy with it. There's another aspect of this that says sometimes the correct solution is to advise the user to upgrade their hardware, and even further down the track, if you really wanted to go there, there's a world in which you could save yourself many hours of developer time trying to optimize the thing by simply shipping the user a better device. Buying a used phone that's a year old or whatever might cost you $300, and that might be way cheaper than paying for a single developer to try to investigate the problem. Okay, so another possible outcome of finding the bottleneck when reported to the user is it isn't actually a performance problem as much as it is a programming error. It manifests as a performance problem, like as far as I can tell from the perspective of somebody using this on my phone, like, when I do this action, it's slow. But the reason why it's slow, let's say, just for the sake of the example, is you're doing an async task on the UI thread, right? It reports the graphical user interface lags, and maybe they get the not responding dialog. Those are not a result of low computational power on the device or being blocked by waiting for disk reads to happen or anything like that. It's just a programming error. right? So the fix there is fix the bug. If you identify that this is the scenario that you're facing, right, we don't have to do any of the performance investigation. You just fix the bug, and then we are all set, right? Just get on with it. Okay, so let's start with considering CPU, right? CPU is probably the easiest to diagnose, and the things that we examine in this course mostly look at this kind of thing, right? So something like HTOP, Task Manager, what have you, will tell you if the CPU is very busy right now. You can look at the percent CPU columns, and you can see where your CPU time is going. So this gives you information about what process or what thread is consuming a lot of CPU. If you look at the simple version of that, though, you only see right now. And what do you see in terms of long-term average? So if you ask using the table of processes tool top here in Linux, this is checking in with a machine that I used to have in my office that was named Loki, which is no longer working, but that's fine. These things only live so long. So it said up 151 days, 23 hours, 38 minutes, 8 users, load average 0.87, 0.92, 0.91. The last three numbers there, 0.87, 0.92, 0.91, are the 1, 5, and 15-minute averages of CPU load. Right? You can look at the immediate CPU load, but that's kind of spiky. These averages give you kind of a better idea of what's going on. Right? Why were the load averages somewhat high for this machine? Well, partly at the time I was donating its free CPU cycles to World Community Grid. I used to say, I'm single-handedly saving the world. And I mean, I did stop in 2016, and I mean, look what's happened since then. So maybe I shouldn't have stopped. But lower numbers mean less CPU usage and a less busy machine overall. How to interpret these numbers? Picture a single core of the CPU as a lane of traffic, and you're a bridge operator, so you need to monitor how many cars are waiting to cross the bridge. If there's no cars, traffic is good and drivers are happy, but if there's a backup of cars, then there will be delays. Right? This breaks down into like three things, right? 0.00 means there's no traffic, so no demand for the CPU at all. Anything between 0.00 and 0.99 means we're under capacity and there will be no delay. There's no waiting for the CPU that needs to happen, right? This doesn't mean like absolutely no waiting ever. If you remember thinking from like an operating systems course, right? And when you have multiple threads and every thread is ready to run and you only have one CPU core, like obviously one thread can be running on that CPU core at a time, but the demand for CPU is below the available capacity of the CPU, which is to say that we have more than enough capacity so that all the threads, when they're ready to run, will get a chance to run and nobody's waiting an excessive amount of time. Right? On the other side of things, if we're at 1.00, everything's okay, but we're at maximum capacity. If even one more car shows up in this analogy, then there will be a bit of a backup and this will cause a delay. Right? Anything above 1.00 means that there is a delay. There are threads that are ready to run, but there's just not enough CPU time for everything because demand exceeds supply. And if we have 2.00 load, that means that we're in a situation where we have twice as much demand as there is supply in terms of CPU time, so the bridge is full, and there's an equal number of cars waiting to get on that bridge. All right, so this is represented here with a neat little diagram in which we have the cars represented as little blue vehicles, and every car represents 0.1 CPU load. So okay, every CPU has 10 spaces, right? And a load of 1.00 means 10 cars appear on that bridge. A load of 0.5 means 5 cars, and there's obviously spaces in between. And then 1.70 says there's 1.0 worth of cars on the bridge, and then 0.7 worth of cars waiting. So being at a load above 1 isn't necessarily bad. There are busier times, and there are good and bad days as far as the CPU is concerned, where workload is a little bit higher or a little bit lower. That's okay, right? But we should be concerned if there's consistent load of 1.0 or above, because it does suggest that we're being limited by a lack of CPU time. If we had more CPU time, then more threads would get to run, and we probably would expect that this is better performance, right? If load is below 1, then we are getting close to it, right? We know how much room we have to scale things up. If we have twice as much CPU capacity as we actually need, then we know that chances are we can handle more users relatively easily, right? But if we're at like 0.7, then it's time to investigate. And sometimes this means we have to do some work to improve our efficiency. Sometimes it just means we need to buy more hardware or buy better hardware, something like that. If we're seeing load at like 5.0 though, that's like a red alert situation. That is an emergency as far as we're concerned, because demand is way higher than supply, so we're probably not providing good service. Like, we're probably not giving a good user experience. If we are this far overloaded, something is seriously wrong. Our workload is out of control. Now that is for a single CPU. So if you have a load of 3.00 on a quad-core CPU, that's perfectly fine, because the total capacity is 4.00 units, and we're only using 75% of the total capacity, right? And to extend the traffic analogy a little bit, right? It's like, what if we have 4 lanes of traffic, and we have 3 lanes used to capacity? That's really the same as if we had a single much bigger lane and 75% utilization in total, right? We could redistribute that workload a bit, and we would probably end up just fine. So that's what's up with CPU. What about memory? If you're using some garbage collected language or framework, one of the signs that we have a problem is that the garbage collector is running a lot, or perhaps is running for a very long time when it does run. That's kind of the best case scenario for something that's garbage collected. If we are seeing a lot of runs of the garbage collector, like, yeah, we are cleaning up a lot of memory. It's concerning that this has to happen so often, but it is getting solved, right? The garbage is getting taken out, and that implies anyway that the system is likely to keep going. It does get worse if we end up with something like a crash or out of memory error, right? That suggests that we're not keeping up in terms of garbage collection, or at the very least, things that are being garbage collected are not enough to keep up with the rate at which new stuff is being allocated. So that would be less than ideal. But maybe we don't have a crash, right? Maybe we end up actually with a swapping kind of situation, because that would be a way to notice that memory is a limiting factor, right? Crash is at the extreme end of what could be going wrong here, where, like, yeah, our system just stops working because it's run out of memory. But it's also possible that we just have a lot of swapping, which results in poor performance, right? If we don't have enough RAM, lots of data is being shuttled to and from disk. This is slow as far as we're concerned, and suggests, in fact, that we need to make some changes to get things to not swap as much. And if this is the case, right, we'll find that by looking at disk utilization. You can ask the table of processes tool top about how much swap is being used, but that's probably not an interesting value. Here's, again, a readout from the same Loki machine. It only had 8 gigs of RAM. This was, I built the machine 10 or 12 years ago at this point, so it's not as crazy for it to have 8 gigs of RAM as it would be if I were building it today, right? But it says a lot of this memory is used, but does that actually tell us anything? Problem is, no, it's not like CPU, right? Memory being full doesn't necessarily indicate anything bad. It does mean the resource is being used to its maximum potential, But there's no benefit to keeping a big block of memory open for no reason, right? That's like stockpiling late days. Like, there's no benefit to that. Every now and again, we get asked in Piazza or similar, like, oh, can we get like a bonus if we didn't use any late days? And like, no, that sort of defeats the purpose of late days, because I mean, at the end of the day, a bonus for not using them is functionally equivalent to a penalty for using them. And the purpose of late days is that you shouldn't be penalized, and for all the various circumstances that happen. You don't feel well, something comes up, there's lots of deliverables from other courses that overlap. Like, all of those things are the reasons why we have late days, and penalizing you for using them absolutely defeats the purpose. So of course we don't want to do that. So using up memory isn't bad. Keeping stuff in RAM is fine. Things move into and out of memory as they need to, and nobody hands out a medal if you reduced the amount of system RAM that was in use. Memory's not like CPU. The CPU goes to an idle state if there's nothing to do, and that's potentially also like a low power mode as far as we're concerned, if it's a mobile device or something where energy consumption is more important. And if that's the case, we don't want to be using it unnecessarily. But memory's not like that. So freeing out of memory appearing full is a little bit like getting all in a knot about how system idle process is consuming all of your CPU. It's like, that's not what it is, and that's not how it works. So we want to look at page faults. And we look at page faults with the command ps-eo, and you can specify you want minor and major page faults. And what we're specifying here is these are the columns that we want returned by the ps command, the one that looks at processes. And we're interested in major and minor page faults. Minor ones are, we copied a page from another process. We didn't have to go get it from disk, but we did have some sort of copy behavior that takes place to move data around in RAM. And then there's major ones, which are we actually had to go get it from disk. And this is process lifetime data. So this is a lot, right? This is lifetime, and so you can have hundreds and thousands of page faults in a long-running process. And the other thing about it is the historical data persists. So you could have a program that has a lot of page faults on startup, and it ends up with a high count, but at steady state, it doesn't have very many page faults, right? We can take a look at this. I've prepared a little demo of what it looks like on one of the ECE servers, so we can actually see some data.
And we can take a look. And we'll see, of course, this is way more data than we could ever possibly need. And for some of these things, we can see somebody running Valgrind something or other here, and there's been 42,472 page faults and stuff like that. This is lifetime, though. So you could have a lot of page faults at the beginning of your program and then nothing for a very long time. And if that is the case, then this information is maybe not that helpful. What you might actually want instead is a report on swapping. And the report on swapping is retrieved by doing vmstat5, and it tells you, based on your process and what have you, about which things are doing swaps. And the swap in and swap out columns are the one to watch for. Unfortunately, in this example, they're not super well aligned, but it's this SI and SO fields here. And they tell you about how much swapping is actually going on. In this example, they're mostly 0, but that's good. You don't want there to be a lot of swapping. This is the slow step if that's what we find. There's a lot of swapping. We're fortunate in this case to see that in our current system, the ECE Tesla system, that's not happening, so no complaints there. If we saw a big number, we would be a bit more upset by that. Keep in mind also, it does have to be a significant number. If you saw just a little bit of swapping, that could be inevitable. Given a sufficiently large problem, it won't be able to all necessarily stay in memory all at the same time, and you would have a little bit of swapping, but a little bit is painful, but not fatal. A lot of swapping is a big concern.
Okay. So what we actually want is the swapping report. That one's more interesting. And here we're going to look at that output from VMstat. In VMstat 5, we're interested in this specific report that's about swapping. And in particular, the columns SI and SO for swap in and swap out, respectively, are the ones to pay attention to. This is good. If we see zeros, right, this is excellent. We're not swapping to disk, and that's not a performance limiting factor, right? A little bit of swapping isn't the end of the world. These things do happen, but it is concerning if we see a lot of it. So here's a different example that not as nice, that has a lot more swap in and swap out kind of behavior, right? But if we're not doing significant swapping, chances are that memory is not holding us back, and we can likely conclude it's not the bottleneck device. All right, so let's take a look at disk. Looking at disk might seem slightly redundant if memory is not the limiting factor, because yeah, truly, if all the data were in memory, then we wouldn't have to go to disk at all. But sometimes that is our bottleneck device. In particular, if we're dealing with magnetic hard drives, then we should be worried about this. And our command for this is iostat, and we can ask for the IO status about a particular device. In this case, /dev/SDA represents the first hard drive device in the machine, and it tells you a whole bunch of stats, but the one that I'm actually interested in here is %util, and in this example, yeah, %util is 1.34, which obviously isn't a lot, and yeah, we know this isn't the limiting factor for our system. Right. If we saw 100%, we would know the disk utilization is at its maximum, and that would be an obvious indicator that it's a limiting factor. Right. It doesn't tell you about what's using it as much as we would see with the CPU, but we can look at what processors are using the I/O subsystems with the command iotop, but that requires root level privileges, which you may or may not have on the machine that you want to evaluate that on. Okay, next idea. What about network? So you can ask about network with nload, which gives the current, average, min, max, and total values. And you get a nice little graph if there's anything to see. It's not so much fun if nothing is happening, because it's just little ASCII arts, dotted line kind of thing. Okay, I guess, right? This kind of thing is sometimes useful, but in this case, the data that we see here, pretty low utilization for the network, right? If we saw that data was leaving at 100 megabits per second, we have a pretty good idea that was the limitation, and you might be network limited on that basis. And you could have something that looks like the maximum theoretical for your Ethernet connection, but you might not, right? What if you're using other hardware? There are these power line devices. If you're living in a place where there aren't Ethernet cables installed in the walls, like one of the ways that you could solve that, of course, is install them. But if it's not your house because you're just renting it, like, what do you do? So you can use like wireless network, but you could also use these power line devices. And these power line devices basically work by adding the networking signal on top of the power signal that runs in the regular AC wall sockets. This does limit your speed based on the condition of the wires in the wall, alongside any other devices of the same circuit that add noise. So what should be 1,000 or 100 megabit might actually look more like 32 megabit or something like that. Is it optimal? I'm going to say no. Might it be better than nothing? Potentially, right? And it might be much less disruptive than trying to run Ethernet cables through the walls, particularly if it's like an industrial building and it's all made of concrete. This isn't a trivial thing to just get a cable from one place to another. right? But wireless networks, aren't magic either, right? They're affected by walls, floors, electromagnetic interference, humidity, how many other wireless networks there are in the area. So chances are you're probably never going to get the maximum theoretical, and you would have to validate whether network is a limiting factor by also considering what's the maximum speed that you can get, right? Speedtest.net is just an example. It's a pretty popular tool for assessing this. And it gives some indication of what the network connection speed is like from a given device. It looks at download and upload speed as well as latency. And you may need to test multiple times to get a realistic picture of speed. Right? And this test does validate the speed of connection to the upstream server, i.e. whatever's operated by the speed test service themselves. That's not necessarily the same thing as connecting to your own data center. Both locations can have good network connections to the outside world, but they might not be able to talk to each other super well. Right? And I've seen this in personal experience. I've seen network speed issues for people who are working in Hong Kong for a data center that was deployed in Frankfurt, Germany. The problem is not bandwidth, but latency. Right? How long it takes for the data to get from one point to another. And we've talked about the difference between those much earlier on in the course, so we don't need to repeat that discussion in detail here. Right? But if you want to get an idea of like the path and the latency between different devices, here's a traceroute tool example. And this isn't my example. I've just taken it from a guide about how to read a traceroute. And so they're trying to traceroute to catchpoint.com, and it results in showing you a bunch of different hops to try to get there. So there's work to resolve catchpoint.com into an IP address, and you can follow along with the various hops. Some of them are just IP addresses, which you can do a little bit more homework to look up sort of where they're geolocated. But others have a bit more sort of user-friendly names, and you can look at those and you can say, that might be like through Illinois, and then Texas, and then Arizona, just by trying to sort of parse the human-friendly names that are associated with the various nodes, right? And this is giving you some guidance about like what route does the data take to get from here to there. And if you're noticing that there's a big delay from one step to another, that's an indication of where the problem lies. And of course, the big delay may be a result of a temporary problem. Could go away. It could be a more permanent one, or it could be an indication of just the limitations of the speed of light. One of the things that we have to contend with is latency can never get down to zero because there's unfortunately just like no getting around this universal speed limit, right? I looked up. There's some data available on this. wondernetwork.com happened to have some data. Use with a grain of salt because it's not perfect. But it says the ping from New York, United States to Lyon, France is 73.21 milliseconds, which represents 83.79% of the speed of light in fiber optic cable. That was a value I measured in August of 2024, right? And that one happened to be the best for these long distance routes. There are certainly ones that are worse. But even if you got to 100% of the speed of light in fiber optic cable, right, that latency would still be non-zero, right? We're crossing the Atlantic Ocean here. It is a significant distance. The speed of light, even in a vacuum, is not instant, and it will take time for data to get where it needs to go. So if you're designing an application and it has to have low latency for all users, right? If you have some users that are in Canada and some that are in Ireland or whatever, it takes 50 milliseconds on average or something latency between the two. You probably need a second data center in Ireland, right? One more thing that can cut into your effective bandwidth is packet loss, and that is data being dropped or corrupted while it's en route. This does require some device along the line to identify that the packets are not as they should be, re-request the needed packets and wait for them to arrive. So there is some extra work that under other circumstances wouldn't need to get done, and it consumes both time and bandwidth to make that happen, right? Why that happens? It could be a result of a device that's dying, it's malfunctioning in some way, or needs replacing. It just can't do the job that we're counting on it to do. That's possible. Another possibility is that it's environmental. You have some wireless connection, and you have packet loss as a result of the physical situation between the device and the base station. And there's maybe a solution to that, switching to wired, or moving the devices, or using different frequencies to try to get around the limitations that we're currently facing as a result of the environmental causes. The last thing that we're going to consider is locks, and we're going to imagine either this results in waiting for locks very frequently or less frequently, but for a long period of time. We've already discussed the idea of appropriate use of locks, where we should use them and where we shouldn't, and granularity and everything like that. And similarly, we're not going to think about deadlock as the nature of the problem that we're looking to solve. What's up with that? Deadlock is a correctness problem rather than a performance problem. And my hope is that this is something that was covered in a prerequisite course that you took, something like ECE 252, SE 350, MTE 241. Hopefully they will have covered the idea of deadlock and deadlock detection, and talked with you about all the details around lock acquisitions and ordering and all the things that you need to do to prevent the deadlock from happening, right? So what we're interested in is, how do we know that we're waiting for locks but not indefinitely? Right. So one potential indication that locking is a problem is unexpectedly low CPU usage that is not otherwise explained by waiting for I/O. That's an indication that we might have a locking problem, because the threads are not ready to run. They are constantly blocked by waiting for lock acquisition. Now, another thing that would indicate that is just seeing a lot of threads showing up as blocked, and we'll notice that behavior pretty quickly. Unlike some of the things that we've discussed, there's no magical lock trace tool that would tell us about critical section locks. And in fact, the pthread library, that's sort of the standard model for locking and managing locks and what have you, doesn't have in the specification anything that would require that sort of traceability for locks, right? There's no implementation requirement that says we need to have that. And maybe that sounds frustrating, right? Maybe that sounds really weird. It seems like the kind of thing that we should expect to be part of the specification, but unfortunately it doesn't exist, so we can't count on it to be there. What do we do? Well, one possibility is we can introduce lock tracing ourselves. We can, put a thing in the log, every time that we want to enter a critical section, and add another entry when we're in it, and then a third one when we leave. It's not great. We've talked about printf debugging and what have you as a thing, and we can, but it's not necessarily ideal. It's not always going to solve our problems. There's a tool, we're going to talk about perf in a little bit, performance tool in Linux, and it has a command perf lock, which seems like it does what we want, but no, it doesn't. Perf lock is for kernel locks only, which helps if you're developing the kernel, and it helps if you're encountering a problem in system calls or something to rule out what's going on there. But it doesn't help us very much with an application program that's encountering this issue. Then there are other tools, commercial tools, like Intel offers vTune, for example, that can allegedly, I haven't used it myself, find these sorts of lock contention problems, but it costs money and it's CPU vendor specific. Do you have an Intel CPU? Maybe, but maybe you don't. And debugging the problem with different hardware maybe requires yet again a different tool. Okay. So with all of that said, right, most profiling tools and most of our discussion from here on out are going to talk about CPU profiling. We will talk about heap profiling and stuff like that. But the most likely problem that we're going to face it's the CPU. And we are going to be using tools to identify what in our code is consuming so much CPU or what's taking so long so that we can make changes to improve it.